Okay, so today we are going to start our last main topic in Poli-Sci 30. It may be the last topic of any size, depending on how things go. It will be the last topic that you will be responsible for on the exam. If we're running ahead 10th week, I will probably spend some of our last lecture talking about strategic voting. Some years we get that far, some years we don't. Okay, but I am going to spend the next, at least the next 3, maybe the next 4 class periods talking about repeated games. Okay, so what I'm going to do is I'm going to pick up a thread that we started to talk about the day we talked about the prisoner's dilemma. Okay, we went through the prisoner's dilemma, observed what a sad story it is indeed when people acting in their own self-interest can arrive at a collective outcome that's worse for all of them. And then in talking about whether people behave that way in real life, one of the strongest objections or counter-arguments that was made to the idea of prisoner's dilemma outcomes actually occurring was that people don't just think about the current game that they're in. That if you're one of those prisoners and you're thinking about whether you want to defect or cooperate, whether you want to give evidence against your buddy or stay silent, you might not just be thinking about the incentives that the DA is giving you, but also about incentives farther down the line. The possibility of your partner's brother beating you up, killing you, various possibilities along that line were floated. And I said then, hold on to that. That's what we're going to talk about at the end of the course, and here we are. That's what we're going to talk about today. We're going to talk today about repeated games. Okay, so let me say right off the bat what I mean by a repeated game, because we've already talked about sequential games where time is passing. First one thing happens, then another thing happens, and even though we didn't get into really long game trees with lots and lots of sequential moves, there are some in the book, and you can imagine those things happening. What makes a game a repeated game is that there are payoffs, and then there's further strategic moves. Okay? So if we have a game that just has a lot of moves to get to the payoff, that's still what we would call a single-shot game. A repeated game is a game where we choose our strategies, the outcome ensues, we get our payoffs, and then we interact again. Okay? So that's what makes it repeated. That's worth putting on the board. A distinction between what is properly called a stage game, okay, or a single shot game. Everything we've done so far has been a single shot game. Once we get our payoffs, we're done thinking about it. Okay? This is in contrast to a repeated game. Okay, a repeated game, we get our payoffs. We really do get payoffs, but then there are another set of choices to make, another set of strategies to make. And what this allows is for the possibility of, I get my payoffs, I see what you did, and I can condition how I'm interacting with you in our second round of interaction. I can use how you acted in the past to figure out how I'm going to act in the present. Okay? And the same logic goes forward as well. When I'm deciding how I'm going to interact with you in the present, I'm going to think about, are you going to retaliate against me in the past? Okay, I'll get some payoffs right now from betraying you, but are you going to have an opportunity to hurt me later? That's what we're going to think about. Okay. The overall narrative here, or the game we're going to focus on when we are doing repeated games, the stage game that we're going to pay attention to, because there's a lot to look at here, our stage game is going to be the prisoner's dilemma. that's not true in game theory in general. You can repeat any games, and there are interesting repeated games that have different stage games. But the game that we're going to think about repeating is the prisoner's dilemma. And the question we're going to be asking is whether the shadow of the future, this is a cliche, I didn't make it up, but it's an evocative cliche, whether the idea that you will reward me in the future or retaliate against me in the future, can that change my behavior today? Can the idea that my partner could reward me for cooperation or punish me for defection sometime in the future overcome the dominant strategy I have to defect in the short run? Okay, that's the problem with the prisoner's dilemma. It's a dominant strategy for me to defect and a dominant strategy for you to defect. There's nothing you can do in a single shot stage game to overcome that, that dominant strategy. Okay? But once we start to repeat it, then you might wonder whether we can get cooperation happening in a Nash equilibrium. Okay? And the answer is going to be yes sometimes. So what we're going to be doing today is I'm going to first show you a set of cases where the shadow of the future isn't enough, where you might think that the shadow of the future would get players to cooperate in a prisoner's dilemma, but it won't work. Okay, so we're going to first have bad news today. Then we're going to start looking for good news in a different situation. Okay, so that's the overall narrative. So the prisoner's dilemma example I'm going to start with is going to be an example of teamwork on some kind of project. Okay, you could think about this as projects that you would do together as students at UCLA, and I think actually that's the example I'm going to use, but it would also work if you thought of it as projects in any kind of workplace. Okay. The quarter system at UCLA is going to make working together as students, I think, a good example for us here. So we're going to think about Bruin A and Bruin B here. And they are working together over 3 quarters. Okay? They are working on a group project that will get them a grade fall quarter, winter quarter, spring quarter, and then they're both graduating. Okay? So what we're thinking about is repeated interaction with a very clear time horizon. Both of these guys know that at the end of spring quarter, they're going elsewhere and that they will never see each other again. And that definiteness part of it, that they're never going to see each other again, that's going to be key to this example. Let's say that one of them knows very much they want to go to the East Coast and the other one is certain to stay in California. Okay, so with that background, what I'm going to do now is I'm going to put up the stage game. And this is going to be repeated 3 times. Okay, so since this is ugly jargon, let me just emphasize. The stage game is whatever game is repeated. Okay, so the stage game here, repeated 3 times. Each person has a strategy that involves slacking off. It's going to have, the same basic structure as cleaning the apartment. All these prisoners' dilemmas have a common logic. That's why they're all prisoners' dilemmas. Bruin A can slack off or work hard. Bruin B, same story. Slack off, work hard. Okay, if they both work hard, it's a good project. Okay, they get payoffs of 3. If they both slack off, it's very bad. They slap something together at the last minute, they get bad grades. Neither of them like it. Okay, I'm Bruin A. Okay, if I work hard and you slack off, my payoff is a -2. The project is not as good as it would have been if you had helped with it, okay? And I worked really hard on it. I spent a lot of time, okay? So slacking off is better for me than working hard if you slacked off. From your point of view, though, okay, maybe we didn't get an A, but we got a B+, and your law school applications have already gone in. You just think that's fine. You did well in your other classes. This is your best outcome. Okay, so standard prisoner's dilemma. Example here, when the roles are reversed, the payoffs are reversed. Okay. So prisoner's dilemma, as in all prisoner's dilemmas, I set it up so that both players have a dominant strategy to slack off. 0 is better than -2, 5 is better than 3, same story here. Touching base with a question I've had in my office, do you have to look for dominant strategies in the prisoner's dilemma? No. If you just do cell-by-cell inspection and look for the Nash equilibria, you'll see that this is the only Nash equilibrium. Okay? That this is indeed a Nash equilibrium because both players would rather have 0 than -2. This can't be a Nash equilibrium for the same reason that you don't want the -2, you'd rather have the 0. Same here, and this cell is not a Nash equilibrium because if we end up here, both players would prefer to have slacked off. Okay, so single Nash equilibrium in the single shot game. Okay, so let's put the stage game Nash equilibrium is slack off, slack off. Okay. But now let's try out this shadow of the future idea. Okay. You've got 3 quarters to work together. Okay. If you could both work hard this quarter, you'd both be better off. And in the next quarter, you could say, yes, and if you worked hard last time, I'm going to work hard this time, and we'll get 3 again. And in the spring quarter, if you've worked hard both quarters, I'm going to work hard in the spring, and we'll get 3 in the spring quarter too. And you could be saying that, and your partner could be seeing the same logic and nodding their head. That's the idea behind the shadow of the future implementing cooperation. Okay? How's that sound as a strategy? Sounds good, right? Okay. People are nodding. Elaine.
So there's one Nash equilibrium that tells you like the dominant strategies of the players. Is that what you're saying? The easier way to do that?
Elaine is saying, is there one Nash equilibrium that tells you the dominant strategy of each player? That is true in the prisoner's dilemma. It's not necessarily true. The generalization of the point I was making here is if you're looking for Nash equilibria, one thing you can do is you can look to see if players have dominant strategies. And if they both have dominant strategies, that will be the Nash equilibrium. Okay? But you can also forget about dominant strategies. You can just look cell by cell to find the Nash equilibrium. Okay? So kind of the take-home message from that is you will never go wrong with cell by cell inspection. And actually, for a lot of the 2x2 games that we're focusing on here, just looking each cell at a time for the Nash equilibrium is often just as easy as looking for a dominant strategy, and you won't go wrong. Where the dominant strategy or iterated dominance becomes a better way to go is if you have a really big payoff matrix and going through every cell just gets really tedious. Okay? So cell-by-cell inspection will give you the Nash equilibrium. It won't tell you whether the Nash equilibria are based on dominant strategies, but in a lot of cases you don't care about that. Okay, so how many people think that this scheme would work? Let's cooperate. Let's decide to cooperate in fall quarter because we can make future cooperation contingent on it, okay? I know you've got an incentive to slack off fall quarter, but I can dangle this reward in front of you that yes, if you work hard this quarter, I'll work hard next quarter and the quarter after that, and you can make the same argument to me. Did you guys go for that? Anybody see any problems with it? You guys aren't going for it because I said it wasn't going to work, and it's not. What is the problem with it?
The incentive to cheat.
What is the incentive to cheat?
Well, if you know the other person's going to work hard, going from the last
David? David says there's an incentive to cheat, and I'm going to amplify one thing that you said. There's an incentive to cheat in the last quarter. Okay, and that's the problem. The problem with having a really clear time horizon is part of this game doesn't have a shadow of the future. If it's fall quarter, there is an incentive to cheat, but I can balance that incentive by saying, you cheat now, I'll cheat next time and you'll be sorry. You do the right thing now, you work hard, and I'll do the right thing in the future and you'll be glad. Okay, so in fall quarter and winter quarter, it's looking pretty good. Spring quarter is the problem. Okay, and to really elaborate this part of the problem, what we're going to do here is we're going to combine the simultaneous part of this repeated game. It does have a simultaneous stage game here with what we learned from sequential games, what we learned about how to solve strategic situations where time is passing. What we learned is to solve it backwards, to think about the last thing that can happen and reason your way forward. Okay, so what I'm going to do here is I'm going to make a different kind of table, not a game matrix, but this table is going to have fall, winter, spring. Okay, and let's see, do I really need to have both players' strategies in here? Why not? Bruin A and Bruin B. Okay, Bruin A and Bruin B, to their regret in this case, took poli-sci 30 last year. And they know in these situations, you look forward, reason backwards. So if Bruin B is making this pitch, yes, let's work hard now because in the future we can reward each other for working hard. Bruin A is going to be looking ahead to spring quarter and thinking, okay, what am I going to do spring quarter? So let's start here. Start in final round, and we're going to reason backwards. Just as with game trees, we start at the bottom and reasoned our way up, it's spring quarter. You are off to Boston. I'm off to San Diego. We're never seeing each other again. You are going to work in the IT industry. I am going to be a family lawyer. Our paths are never going to cross again. It's spring quarter. You've cooperated with me, perhaps, in the past. What am I going to do spring quarter? I'm going to slack off, right? I'm going to have senioritis, whatever you want to call it. You might want to call it a dominant strategy. In the spring quarter, there is no shadow of the future. Okay? There is nothing in the last round that is counterbalancing our dominant strategy. Okay? So guess what? We're both going to play our dominant strategy. Okay, well, so maybe we'll just have senioritis in the spring. Let's think about winter quarter, though. Now it's winter quarter, and Bruin B is saying to Bruin A, work hard this time. Work hard this time, and I promise I'll work hard next time. Okay? And we can get to this good outcome. Are you going to buy it? No. That's the problem. This final period, senioritis, lame duck effect that happens in the last round is going to bubble its way back up. Okay? I'm not going to believe that if I work hard this time, you're going to work hard in the spring, because I know in the spring you have a dominant strategy to slack off, and I know there's nothing counterbalancing that. I know that we have no future at that point. So why should I believe that you would make good on this promise? I'm not going to, and you're not either. Okay? So this problem bubbles up into winter, and it bubbles up into fall, too. Okay? We would both slack off in winter because we would realize that come spring, there is nothing to keep us working hard here. In the spring, we're going to follow our dominant strategy. So in the winter, the same thing's going to happen. Okay? So right off the bat, here's our depressing piece of news. When there is a clear, definite end to our interaction, the shadow of the future does not support cooperation. Okay? Translating this into more the jargon of game theory, what you'll read in your book and what you may well hear in other classes, this point comes up a lot in IR classes, is that in the finitely repeated prisoner's dilemma, when finitely repeated, when we have sort of a clear endpoint, cooperation cannot be sustained as part of a Nash equilibrium. Like I say, that's the jargon version. The ordinary language version of that is when we know exactly when we're going to stop interacting with each other, we're not going to be able to use a shadow of the future argument to support cooperation. So a while ago, it was actually more than a decade ago, when California and most of the other states in the early 90s had a flurry of adopting term limits for their state legislatures. Really from like 90 to 94, that went from being a very unusual thing to being very, very common. One of the arguments that was made against term limits was precisely this one. Okay? You want legislators to cooperate with each other. If legislators won't cooperate with each other, budgets don't get passed, government is in gridlock. It's a bad situation if legislators won't occasionally make a choice that works against their individual incentives but is good for the group. And when you have this clear 2 terms, you're out of the legislature incentive, people would argue that that undermined any incentive to cooperate. Now, I don't think it's worked out that way because even with term limits, the people who are in the state legislature interact with each other after they leave the state legislature. They may run for the other house, they may run for other office, they may be involved in politics in other ways. So while the particular doom and gloom story associated with term limits didn't come true, one thing that certainly did happen around that time was that the importance of parties in recruiting candidates really, really increased. Now, there may have been other factors that were affecting that as well. If you get 5 political scientists in a room, you'll get 5 different theories about why partisan politics in the U.S. is so much more polarized today than it was, say, 20 years ago. But term limiting state legislative offices, where those offices are a very important step in a person's decision to become a career politician versus somebody who's maybe participating in local government for a short time and then leaving politics, term limiting at that critical stage does seem to be something that increased partisanship. Okay? So maybe a broader lesson from that is that the potential for eliminating any incentive that legislators would have to cooperate in the legislature was so scary to everybody that some other institution filled the vacuum there, and the parties as organizations would seem to be the candidate there. Okay, so I don't know if I'm digressing or making it more concrete, but the bottom line here is the shadow of the future doesn't work if we know when we're going to stop seeing each other. Okay? All right. So I've got the word finite up here, too. And you might be thinking, well, the number of rounds of repetition always has to be finite. We don't live forever. We're never going to have an infinitely repeated game. Right? That's obviously true. Okay? Nonetheless, the way that we think most productively about repeated games is to think about a potentially infinite repeated interaction. Okay? Potentially in the sense that we don't know when our last interaction is going to be. We don't know that we'll never see each other again. As long as there's any uncertainty about when we're going to stop interacting with each other, we could think of that as something that's potentially going on forever, but at each stage, there's some probability, between 0 and 1, some probability that this stage might be our last. We'll never know for sure. Okay? As long as there is some potential that we'll see each other again, then we're going to think about the game as being what we would call an infinitely repeated game. The idea is never that the repetitions actually go on for infinity, but when we say it's an infinite game, what we mean is we cannot identify the last period. When we're picking our strategies, picking our actions, in a particular period, we don't know if we're going to interact with that player again. Okay? That's going to change things. The whole logic here of why in the last period, nothing would offset the dominant strategy. That whole logic depended on us being absolutely certain here that this was the last time we would see each other. Okay? As long as there's any uncertainty about that. Maybe you'll move back from Boston. Maybe I'll change careers. Then, as long as there's some possibility that I'll remember if you did a bad thing, and I'll also remember if you did a good thing, then there is a shadow of the future. There is some possibility of future rewards. Okay, remember, literally, this is the reward payoff in the prisoner's dilemma. These future rewards can offset the dominant strategy incentive to slack off. Okay? Can offset. I didn't say will offset. So the main thing we're going to be doing when we are studying repeated interaction is to be looking at when the shadow of the future, this idea that if I know you've been a good guy in the past, that's going to give me an incentive to treat you well in the present, and the possibility that you'll remember if I'm a bad guy in the present will keep me from doing that because you'll have an opportunity to punish me for that. Okay? There's going to be another point to that. We'll see. The point will emerge here. Okay. Oh, the point was sometimes that will be true and sometimes it won't, right? Sometimes the temptation to follow the dominant strategy, to slack off, will overcome the possibility of future rewards. If I think it's really unlikely that we ever see each other again, or the temptation to defect right now is just really, really strong, I just get a really big payoff out of it, then it might be true that even when we're repeating the prisoner's dilemma, we're still going to end up at this cruddy Pareto inferior equilibrium. But sometimes the shadow of the future will be enough. Sometimes concern with having a reputation for being a cooperator can be enough to support cooperation. That idea of reputation, I think, is important enough, and I'm going to just put it up here. Okay. When we have that indefinite time horizon where we don't know that we'll never see each other again, then our reputations matter. And what I precisely mean by a reputation in game theory is how I've acted in previous rounds of the game. Okay. That whole thing is. This is the black pen I'm trying to avoid. We're going to hide it over here for some other professor. Hopefully not. We're going to use green. Okay. Reputation means how a player has behaved. What choices did they make in previous rounds? Okay. In previous iterations of the stage game. Okay. In repeated games, players have a history. Okay. And that concern with having a history, having a good reputation, will affect their strategic choices. All right. Okay. So now we need to do a little digression here. Okay. The big question we're interested in is whether a reward in the future for going against my short-term incentives is going to be enough. Okay. How big of a reward from some future interaction that might not even happen, how big does that potential reward have to be to get me to go against my dominant strategy now? In order to answer that question, we're going to have to compare payoffs across time. Okay? And things get complicated there. What we're going to have to deal with is, I guess I'm just going to say it as a fact, the widespread phenomena, maybe that's how I want to say it, that people don't like to wait for things. People like to get their good payoffs sooner. Okay? People are impatient. And I think that's very widespread. One thing I could do is just assert it's part of human nature, and some of you might agree with me just on the basis of that. Another point I might make is, are people impatient? Do they always want their stuff sooner? Well, anyone can get run over by a bus. You know, things can always happen. You're never sure you're going to be around for the future. Okay? That promise of, yes, it'll be so great, I'll reward you in the future, we'll both cooperate, we'll get that reward payoff all the time, you just can't be sure. Okay? Nobody lives forever. We never know when our number is up. Okay? So the general problem here is that, I'm not even say benefits. Payoffs are worth less if you have to wait. Okay? Actually, in my mind, the real source of impatience in people is this idea of uncertainty. That I do think impatience is part of human nature, but I think it's part of human nature because of this fact that we live finite lives, that we may not be around for future iterations of this potentially infinite game. More concrete aspects of social life that can reinforce this would be if your payoffs are money and you get your money sooner, you can invest it and end up with more money at the end than if you have to wait. If your payoffs are not money, but there's something that is worthwhile to you in your current situation, your life could change in a way that would make the benefit not worth as much. So for example, if you're a politician and your incentive to cooperate with another politician depends on campaign contributions, endorsements, good press, good relations with party leadership, all of those kinds of things are worth it to you if you stay in politics. They're not worth so much if you go out of politics. Okay, so the farther in the future you have to wait for your benefits, the more likely that your life will change in a way that something that you care about now will be something you don't care about in the future. Okay. So the way we deal with this problem of impatience, this need of comparing payoffs across time. I'm going to clean up my elaboration space here. What we have to do is we have to account for what's called time preference, or in the sense of I'm just giving another name to the same thing, or impatience. Okay? I think I'm going to switch for this part of the lecture today to thinking about the benefits as being money. Okay? $1 today is worth more than a promise that you're going to get $1 in a year. Okay? That's what we need to account for. Okay. And with a money example, it could be worth more today precisely because of the interest thing, but all of those other sources of time preference also matter. You might not be around in a year. In a year, you might have become a Buddhist monk and you don't care about money. There's all sorts of reasons why you'd rather have your dollar right now. Okay? So the way we account for this, okay, the way we put this into game theory is, as with calculating expected value, we handle time preference in a very standard way, the way it's handled in economics, in business, in public policy, in any domain where we have to compare payoffs across time. The way we do it is with either a discount factor or a discount rate. And I'm going to talk about discount factors mostly. I'll say a little bit in a few minutes about discount rate. They're really just different ways of looking at the same thing. Okay. A discount factor. So what can I say about a discount factor? Okay, so first of all, in political science, we think about discount factors as mostly being part of your preferences. Okay, it just says something, maybe they're induced preferences, it's something that reflects your environment and your overall incentive, maybe it just reflects something purely about you, but it's a characteristic of a player. Okay, it's part of the player's preferences. Okay. Discount factors are usually represented with the lowercase Greek letter delta. Okay, this is a lowercase delta. Kind of squiggly little upside down balloon guy here. Discount factors make sense if they are between 0 and 1. Okay? And let me sort of write down the equation that defines a discount factor. The present value of, let's just do it with $1 received one period. I'm being vague about the time period. Is it a day? Is it a year? Whatever. That we can just adjust the discount factor to whatever is appropriate, is delta. Okay? If you want to make it more general and say the present value of X dollars, it's delta times X. Okay, so let's look at the fact that delta is a number between 0 and 1 here. As it goes toward 1, the person is more patient. Okay? value of future benefits is higher. Okay? Delta is 0.8. That's saying, what is the promise of getting $1 in a year worth to me? Well, it's worth 80 cents. So my discount factor increases up to 0.99. I'm becoming a more patient person. Okay? It's still $1 in a year that we're talking about, but now it's worth more to me. It's worth 99, since it's keeping most of its value, even though I have to wait for it. As we go, so the discount factor gets close to 0, what we're saying is that the person is becoming less patient, future less important than the present. Okay. My discount factor is 0.2. That's saying that $1 today is $1 a year in the future is only worth 20 cents to me today. Okay, I want it now. We, and in this class and in virtually all normal applications of discount factors, are going to think about discount factors that are strictly between 0 and 1. We're not going to think about them being equal to 0 or equal to 1, except as limiting cases. So let's think about what that would imply intuitively. If I say my discount factor is 0, what I'm saying is there is no future. If I don't get it now, I don't care about it. Okay? Discount factor equals 0 means I just care about the present. I never think about the future, no matter how big. If you're offering me $1 million tomorrow, that ain't worth nothing to me now because my discount factor is 0. I live in the present. Okay. People say things like that sometimes. I usually think it's empty rhetoric. Okay. I believe that people can be really impatient sometimes. I certainly believe the discount factors can get really low and that people can put not very much weight on the future, but absolutely no weight. Sorry. Tell me another one. All right. Same story, though, at the other extreme. If I say my discount factor is equal to 1, I'm saying I have no time preference at all. You can make me wait 1,000,000 years for my $1, and it's worth $1 to me today. Okay, that also sounds truly implausible. Just as I can believe discount factors getting very close to 0, I can imagine them getting very close to 1. I don't know about 0.99, but I can imagine people caring a lot about the future. Okay? But not to the point where the future is as important as the present. Okay. So what we're going to do is we're going to be using these discount factors in our repeated game to allow us to compare things that we get right now, okay, often our extra benefit from defecting in a prisoner's dilemma, with some future benefit, okay, the possibility that we'll get a higher payoff because we'll both do the cooperative thing in the future, okay. When we do that, we have to take account of the fact that those future benefits, that the shadow of the future is discounted. Discounted because of time preference. Okay? And we account for this with the discount factor. All right, so I want to see a couple of things about discount factors. Now, one point I want to emphasize is the discount factors we're using in game theory, they work just like discount factors that you might encounter if you take a finance class, if you take economics classes, if you take public policy classes. Discount factors are used a lot in the real world. Discount factors are sometimes written into law by Congress, when Congress is writing a law and giving agencies like the EPA or the FDA or all of these other agencies that set policy in areas that require balancing costs and benefits sometimes Congress will actually say, and a discount factor of 0.9 or something like that shall be applied to cost-benefit calculations. Okay? Management consultants or other sets of people that have to use discount factors to recommend one kind of policy versus another kind of policy to the firms that they work for. Managers have to think about this. So in real life, these are numbers that lots and lots of people are working with on their computers in their spreadsheets. Okay, so it's one of the places where game theoretic reasoning really hooks up with some very substantive real-world analysis. Okay, that's one point that I want to make about it. Another point I want to make is I want to get back to this business about discount rates. Okay, so discount factors, I'm going to use discount factors. When we use them in political science, I find them easiest to use because they, to me, they're the simple way to explain this. How much less is something worth because I have to wait for it? The discount factor puts a number on that. How much less is that dollar worth by the fact I have to wait for it? If my discount factor is 0.6, that's what it's worth. What the dollar today is worth 0.6. Because in many of these concrete applications of discounting, the time preference comes from money and from foregone interest, okay? All those managers in firms and those financial analysts that are using discount factors to recommend one type of investment or another, one type of project over another, because their time preference comes so much from interest rates, they are likely to use discount rates, okay? So discount rate is the fraction by which my payoff, often money in this context, increases if I get it sooner. Okay. So the discount factor draws our attention to things being worth less in the present. The discount rate draws our attention to the fact that they're worth more in the future if we get control of them in the present. The discount rate is exactly an interest rate. Okay? So what I want to do is use this board, I guess. Okay. I want to belabor this present value calculation both in terms of the discount factor and the discount rate. Okay? So if I'm sitting here at time 1 and the amount I have is x0, okay, but I'm going to get x1 in a year, what we would say here is x0 is the present value of x1. Okay, this is just really an equation that's making the same statement I've been making over and over again. If I have to wait one period for x1, what's it worth to me today? Okay, I'm putting a variable on that. I'm calling it x0. And what it's worth to me is how much I'll get in the future times the discount factor. Okay. Another way we could frame that, though, is how much do we have to invest now, period 0, to get x1 in the future. Okay. Discount rates are usually symbolized by R. That R for rate is often used for interest rates as well. Okay, well, we can do that same thing. Okay, so if I have x0 now, and what I need is x1, in a year I'm still going to have my x0, and if I'm getting interest on it, okay, if there's some amount that it's increasing by the fact that I'm getting it now rather than later, this is the amount. Okay, if it's the interest rate and I want to have $5 in the future, the way to find out how much I need now is to put the real interest rate in here and solve for x0. Okay? Okay. So the other way we could say this, we said x0 is the present value of x1. We could also say that x1 is the future value of x0. Okay? What I hope you're seeing is that these two equations are saying the same thing in different ways. Okay? One is thinking in terms of what we want to have in the future and what it's worth today. The other you could think of, no, this one is the one that's thinking in terms of what we want in the future and what we need today. This is in terms of what we have today and what that translates into in the future. Okay? So because they say the same things, we can actually derive the relationship between the discount factor and the discount rate here. Okay? So do I want to do that? Yeah. Okay. What I'm going to do is I'm just going to divide through this equation by 1 over 1 plus r. I'll get x0 equals x1 divided by 1 plus r. And what that is telling me is, look at these two. Delta has to be 1 over 1 plus r. So if you're given a discount factor, you know the discount rate. If you're given a discount rate, you know the discount factor. They're just different ways of approaching the same idea. We have to belabor this because both are used. Discount factors are used most in political science. They are used ubiquitously in international relations, which, as I've said, is the main place this stuff gets applied. Discount rates are used more often in economic applications. They're used more often when the source of the time preference is foregone interest rates. Dixon and Skeeth use the discount rate. I'm using the discount factor. As I say, discount factor seems easier to me. You're more likely to encounter it in your other political science classes, but you need to be able to work with both of them. And the thing you need to have to pay attention to is that when a discount factor gets high, it means the person is more patient. As R gets high, it means the person is more impatient, right? The higher the interest rate, the more I want my money now, okay? Because the more it's going to increase if I invest it. And if the interest rate is low, the person is getting less patient. It's the opposite with discount factors. Okay? A discount factor, just the way it's set up, as the discount factor approaches 1, that's saying, oh yes, the benefits I'm getting in the future are worth almost as much as I was getting them right now. I'm a very patient person. As it's getting low, going towards 0, it means, yeah, those benefits I'm getting in the future are worth very little to me. I really don't care about them. I'm more impatient. And you see that here, right? R is down here in the denominator of delta, and as R goes up, delta goes down. Is there? Oh, thank you. Good. Okay. right with the bell. Did you notice that? I'm right on my schedule here. Okay, so R gets high, the person is more impatient. Let's stick with that and say less impatient. Double negatives get me every time. R gets high, the person is less patient, more impatient. Okay. All right. All right. The one final thing I want to say, actually, let me just ask you guys, how many of you have done present values in other classes, even like in high school or? Yeah. Fewer than I would have thought, unless you're just holding back on me. Okay. Okay, good. Good that you are learning it here. It's a really valuable thing to be able to think about, to be able to think systematically about this problem of time preference. It's a part of life that we're always having to deal with time passing, and discount factors are a good way to do that. So the one other thing I have to add here is how discount factors apply for longer time horizons. That's something I've been kind of sneaking in to you guys, saying if I have to wait 1,000,000 years, if I say my discount factor is 1, then I think it's still worth exactly what it is, as if I got it today. I use that as an example of why a discount factor that was strictly equal to 1 would be unrealistic. But so far I've only talked about having to wait 1 year, 1 period. Okay, so let's do the final generalization here. Okay, the present value of X benefits, X utility, X dollars, X payoff, X anything, T years, T, trying to be general here, so let's not even say years, T periods in the future is delta to the T power times X. Okay? And to see that, let's just kind of put in some numbers here. Let's think about X in 2 periods. Okay? So if I have to wait 2 years to get my X, okay, well, I'm going to get X in year 2. What's that promise of getting X in year 2 worth to me in year 1? Okay, this is the value in year 1. Okay, because in year 1, I'm only going to have to wait 1 more year till I get it. What's that worth to me right now in year 0? Delta times that. Value in the present. Okay. So here I am in year 0. I want to know how I should compare this X that I'm going to get in 2 years to things I'm getting right now. How much would I be willing to give up to get them? The way I think about it, there's kind of a working backwards, look forward, reasoning backward aspect to this as well. I'm going to say, well, 1 year from now, when I've waited half the amount of the time that I have to wait for my X, I'm only going to have 1 more year to wait, and I know what that value is. That's my discount factor times whatever X is. So that's a number. What's that number worth, that value that I'm going to get a year from now worth to me? It's delta times that. Okay, so for 2 years, delta squared X. 3 years, the same story. Any number of periods, this is how you account for it. You raise the discount factor to the power represented by the number of rounds you have to wait for the benefits. Okay. So again, this kind of calculation is like the life of a public policy analyst. If you are doing policy analysis for a think tank, a government, what you are constantly needing to compare is often costs that you have to pay right now, costs up front of building new schools, changing a hiring plan, allowing charter schools, all of those kinds of things. And then you're going to have to compare those current costs against benefits that are going to, some of which are going to happen in a couple of years, some of which you're going to have to wait 10 years for, others that might have longer time horizons. You have to balance these different time horizons, and the way people do it is with discount factors. Okay? What real people in the real world do is they are solving problems that sound like poli-sci 30 homework problems. How big would your discount factor have to be to make one project a good idea or a bad idea? So we don't, in many cases, we don't actually know what our discount factor should be, but we can figure out how high it has to be to change a decision. So that kind of looking for a cut point on this side, the present value is too low. On that side of some critical value of the discount factor, it's too high. Okay. So questions on discounting? Yes, Elaine.
Are you saying that that's how much these taxes work to you today? You're going to get it 2 periods from now?
Yes, that's right. That's right. Okay. If it's x in 7 periods, it's delta to the 7th power times x. And if you just kind of think in your head about numbers less than 1, when you start multiplying them together, they can get very small very quickly. Okay? So once you get 7 periods out, those benefits for many discount factors are going to be real, real small compared with what you've got today. Okay? Does that sound like a reasonable way to represent time preference to you guys? Pretty reasonable, you guys are like whatever at this point. I think it is reasonable. It's done a lot, as I've said, in the real world by professionals who are trying to make decisions that are right for their company, that they think are right for society, that are good decisions in one way or another. Psychologists say, though, it's not actually the way people in their ordinary life make decisions. Okay? If you go into the lab and try to look at how people handle time preference, they are more impatient than what this implies. Okay? And I just said in response to Elaine's question, which is what made me think of this, that if you're multiplying, taking 0.8 to the 7th power, you're going to get to a pretty small number there. So something that you have to wait for is really, really going to be discounted a lot if you have to wait 7 years. The reality psychologists say is people are even worse than that. That people are much closer than we'd like to think to that only the present matters. Okay? That in reality, what people do is called hyperbolic discounting. And it involves more impatience, or it reflects more impatience than the discounting formula. Okay, so this is one area, really I would say of kind of current research in psychology, and it's a place where this discounting logic that's come out of economics and finance and bubbled through game theory and political economy has been very helpful in psychology, even though the psychologists tell us it's wrong, because it gave the psychologists this very clear baseline to compare real human behavior against. Okay, so that's kind of an exciting thing. All right. So I'm going to end today. I want to say one thing about this week's notes, though, which I will post by tomorrow afternoon. This week's notes has 2 sections that I haven't gone over in class because it's easy stuff, okay? There are two places, I'll shade them, I think it's colorful in the notes. One thing that is in the notes that I'd really encourage you to work through is just an example of changing play from sequential to simultaneous. Remember I said we didn't need to do that on Tuesday? We didn't. There's also, at the end of the notes, an example of applying discounting just to decisions, okay? Deciding whether a project is worth the cost or not worth the cost using discounting. So especially if you're new to using these discount factors, work through that.